virtual demonstrations for these simplified harness methods. And also, last but not least, is the conclusion. I'm sorry, I have to stop this presentation for a while because I seen comment from the audience. Cik Iza, maybe you can check on this. Is it okay now? Can participant hear the sound? Okay. All right. All right. So let's start again. So overview of today's presentations. I will introduce to the graphene oxide, which is in short we call it GO, and the discovery of and histories of graphene oxide. Next, we are going to talk about harness methods, and we move on to advantages and applications of graphene, and the synthesis introduction for the synthesis of graphene oxide by simplified harness methods. And we are going to look at the characterizations of graphene oxide. And the most important will be the visual demonstration, how we can synthesize graphene oxide by using simplified harness methods. And last but not least is the conclusions from this presentation today. Okay, what is graphene oxide? Graphene oxide is a monomolecular sheets of graphite oxide. So it is a chemical compound that contains carbon, oxygens, and also hydrogens in a variable ratio, which can be obtained by treating graphite flake with the strong oxidizer agent, for example, potassium permanganate. And this graphene oxide sheet is an oxidized analogy to graphene that recently have been received attractive substantial interest as a possible intermediate or precursor in order to obtain large scale of graphenes or manufacture of graphene. So in this presentation today, you will hear more terms about graphene oxide, graphite oxide, and also graphene. So I will introduce to all the participants what is the differentiates between these four terms later on. So the discovery of graphene. So synthesis, graphene can be essentially synthesis by two main category, which is bottom-up methods or bottom-up approach that can be a simple carbon molecule that are used to construct pristine graphene. And this bottom-up approach includes a chemical vapor deposition, uh, plasma-enhanced chemical vapor depositions, epithelial growth on silicon carbide wafer, and etc. However, this bottom-up approach having disadvantages. It is time-consuming and also face challenges for scalability. And the second approach is the top-down method, where layer of graphene derivative are extracted from a carbon source, typically graphite. An example is including mechanical cleavage, chemical oxidations, electrochemical treatments, and so on. So top-down methods are most popular for realizing graphene oxide, graphene derivative, particularly for use in nanocomposite material. So the most popular methods can be employed to synthesize graphene, which is call it as a chemical oxidations of graphite. So next we look at to the history of graphene oxide. The first synthesis of graphene oxide is often attributed to Brody, Staudinger, and also Hammers and Offerman method. So each of these are derived from graphite oxide via the oxidations of graphite using these various techniques. So the graphene oxide was first prepared by English chemist Benjamin C. Brodie in 1859 by treating graphite with a mixture of potassium perchloride and also fuming nitric acid. And later, Soudermeyer further adjust the consistency of graphene component via additions of sulfuric acid that rendering the process with the fast completions in a single vessel reaction. And it can improve the process of the processing yield. However, the it will it not cannot like fasten the process, but in maintaining the longer processing time and also producing hazard gases, for example, toxic gases. And later in 1957, Hammers and Offerman developed a more safer, quicker, and more efficient process that called the Hammers method. So by using a mixture of sulfuric acid, sodium nitrate, and also potassium permanganate as a oxidizing agent. And this method still have been used until today with a slightly changes in terms of mixture of acid. So next, okay, if we look at to this schematic diagram for the preparations of graphene oxide via Hammers or Fermat methods, we can see that there is started the initial elements that use or raw elements that use is graphite. So what is graphite? Graphite is actually a pure crystalline carbon, and it was discovered in 15th centuries in Cedar Wales, and that time farmers are using this graphite as just a marker to mark their sheep for livestock. And then later on, when we are discovered this graphite, we then start to synthesis graphene oxide. Then again, the Hammers method stress on three stages, as you can see from this diagram: step 1, step 2, and step 3. And these three stages are related to the temperature. So we need to uh, control the temperature, which is reactions at low temperature, below than 5 degrees C for intercalations, and mid temperature around 35 degrees C for oxidation to happen, to occur for graphite of the graphite intercalation compound, and the higher temperature about 98 degrees C. This is for hydrolysis of consequences. So, but later it will straightforward exfoliation where a single graphene oxide sheet can be obtained by full exfoliations of graphite oxide. So this is the graphite, the black color. And when we undergo the oxidation process by introducing the strong oxidation agents, as I mentioned earlier, which is potassium permanganate, you also can refer this figure. Graphite, when we introduce oxidation agent, which is potassium permanganate and mixture of acid, and then we are expand the graphite into graphite oxide. And later on, in order to have a full exfoliation, we need a mechanical peeling. So this mechanical peeling can be done via sonication, swirling, and that can turn graphite oxide into graphene graphene oxide. So the color also can be observed in this diagram here. Graphite oxide suspensions, which is standard at the bottom of the vial, where after undergo sonication, you can see that it's quite homogeneous with the color of brownish. This is in the aqueous dispersion. So why Hammers methods? Hammers and Offermans actually made a numbers of improvement as compared to previous one, as compared to Brodie and also Standermeyer, when he introduced a more safer technique, including the use of potassium permanganate as oxidizer rather than use the potassium perchloride, which is hazardous and that can evolve the toxic gases during this process, and also additions of sodium nitrate to form the acid rather than to use nitric acid for as a solvent, so which is quite dangerous because nitric acid is a strong acid. And due to this safer and more scalable nature of Hamer's method, this is one of the general method that being used. And in most cases, okay, it can be slightly altered in order to generate graphene oxide. So the alterations of Hamer's methods as shown in this diagram here. All right, as we can see from this schematic, most of the common graphene oxide synthesis can be modified and also can be improved. So the common one they are using uh, potassium permanganate and also mixture of acid that can produce the uh, acidic gases. But any method which can change or improve opens the synthesis route proposed by Hammers is known as modified Hammers method. However, the exact meaning of this term is far from the standard, where in general, carbon source often we use is a graphite flake or graphite powder. It's put into a pronated solvent, as mentioned previous, sulfuric acid, phosphoric acid, or also some mixture of these two acids, and a strong oxidation agent, usually potassium permanganate, is introduced. And another popular modification of Hammers method is improved Hammers method. This one, which is they are removing sodium nitrite with the addition of phosphoric acid. As you can see, the sodium nitrite is removed to phosphoric acid, and this increment of and also increase the increment amount of potassium permanganate up to 3 grams. So the improvements involve no toxic gas, so that can provide, and it also can provide easy temperature controls. And in the result, graphene oxide powder with higher degree of oxidation can be obtained. So this is the method that we are going to demonstrate today, but with slightly simplifications that will be improved. So the overall synthesis route can be modified to fit an individual research need. So next, we are going to see what is the method for the modified Hammers method. So it will contain 3 major steps that involve in the modified Hammers method, which is oxidations, reduction, and post-treatments. In oxidation, it's just normal like a previous one. It's just we are straightly use strong acid and also um, potassium permanganate as oxidizing agent, and we can keep stirring at a room temperature, and then the solution will be overnight, keep overnight after uh, for about 3 days, and after that we can stop the reaction by adding hydrogen peroxide and also deionized water. And later on, the centrifugations can be done for dilution until we reach the pH around 7. And to get the monolayer of graphene oxide, undergo, we can process the solution through ultrasonication methods. And for the reductions, it can be done by adding reducing agent, for example, hydrazines, in order to reduce graphene oxide into reduced graphene oxide. And this graphene oxide also can be functionalized by attached functionalized group to enhance the exfoliation for a certain polar, so it can be dissolved in organic and inorganic compound. And it also can be reduced by introductions of thermal which is we are using thermal reductions that can give a better quality of reduced graphene oxide or graphene. And the post treatment is this one is actually in order for us to get the dry graphene powder. We can dry it in the ovens and then grind it in order to have a powder form with a fine structure. And later it's ready for a characterization test. Okay, now let's look at to the structure of graphene oxide. So graphene oxide layer is about 1.1 plus minus 0.2 nanometer thick. So through scanning tunneling microscopy, STM, it shows that they have local regions where oxygen atom is arranged in the rectangular patterns. So as a structure that proposed here in 1998, there has a graphene oxide has have three groups that attach to it, which is the denoted by A is epoxy bridge, and B is hydroxyl group, and C, which is a carbonyl and a carboxyl group that attach to the edge of each layer of graphene oxide. Okay, advantages of graphene oxide. Graphene oxide can be easily dispersed in water and also other organic solvent due to the presence of oxygen functionality, which means it can help in the mixing of the material, for example, with polymer, with ceramic matrices that can be used in order to improve their electrical and also mechanical properties. A second advantage of graphene oxide is that it can be electrical insulator. This is due to the disruptions of sp2 bonding network. And then, however, in order to recover this honey lattice structure for a better electrical conductivity, we can reduce graphene oxide to reduce graphene, or some they call it as a graphene. So this reduced graphene oxide, however, having a difficulty for dispersion because of lacking the oxygen functionalities. And the third advantages of functionalization of graphene oxide, it can change the fundamental of graphene oxide properties, and it can be suited to your desired application. For example, it can be used in photoelectronic, bio devices, or even in drug delivery materials. And this is can be done by introducing substitute amine group to functionalize the graphene oxide. And it also can increase the dispersibility of this chemical modified graphene in organic solvent, for example, DMF, NMP, and so on. All right. So let's look at to the applications. So overall, to consider on considerations on how we should modify Hammers method is actually must be suited to the graphene-based application. So besides that, the individual researcher should also consider the carbon source, which is graphite that we use, the requirement of the pre-treatment methods, how strong the oxidizing agents, and also the choice of protonated solvent. For example, just now we are using phosphoric acid, sulfuric acid, nitric acid. So this is also important to be choose. And as these all factor can strongly impact the carbon to oxygen ratio of the final product for the graphene oxide. So as you can see from this diagram here, most of the potential applications are contributed from graphene base rather than graphene oxide. This is happened because that graphene is more conductive as compared to graphene oxide. So today we are going to talk about the oxidation, which is a process when we are going to oxidize graphite into graphite oxide. Okay, other than that, there are a few properties that we need to consider in order to achieve or in order to employ the potential applications. For example, larger graphene oxide sheet. So, as a previous research, through this oxidation process, we can have a larger graphene oxide sheets up to 256 micrometer. And the second properties that we need to consider also the shape, which is the dimension, lateral dimensions of graphene oxide. And the third one is this the properties that we need to consider is the level of solubility or level of dispersibility of graphene oxide in a desired solvent. Is either we are going to use for organic or inorganic solvents. And the last, and this is the most important properties for the consideration, is that how we can improve the mechanical strength, conductivity, and also the optical properties of graphene oxide nanosheets in order to achieve our goal for the application later on. So this key design factor in a graphene oxide reduction is depending on the application of the end of the end product. Okay, so let's look at to our main topic today, which is a synthesis graphene oxide by simplified Hammers methods. So this method has been introduced by my former supervisor, Professor Huang Mei, during my master study and also my PhD study in year 2010. So this simplified Hammers method does not involve controlling temperature. As I mentioned earlier, we have three stages of controlling temperature. We need to have 5 degrees C, and then also certain 35 degrees C or 36 degrees C up to 100 degrees C in order for a process to be done. But in simplified Hammers method, it doesn't involve controlling temperature during the chemical oxidations of graphite. So unlike the common practice as previous process, like a Brody and Staudemer, it need the ice bath in order to control the initial additions of potassium permanganate and also heating during the oxidation stage. And we can say that this simplified approach is hassle-free, and it has a slightly exothermic heating during the oxidation process. Um, for example, like during this process, when we pour this solution after the 72 days of mixture into the hydrogen peroxide in order to stop the reaction, it will have slightly increase in temperature up to 50 to 60 degrees C. However, this process will be cooled down naturally in very short time. So we don't have to worry about the increments in temperatures. So these experiments is relatively safe and can also reduce danger of explosions significantly, and in contrast to the normal route of the chemical oxidations of graphite. Okay, so what kind of characterizations that we can do or we can test to analyze graphene oxide? There are a few characterization that involve microscopic thermal analysis and also spectroscopy characterizations. Um, okay, as you can see here, there's a lot of characterization that can be done. However, for today's presentation, I'm only introduced a common technique to characterize graphene oxide sample in a simple way. All right, the first one is the UV visible spectroscopy. So most of the tools are used like UV, SRD, what else? FISEMS is actually a common common tools that we can found in our lab, and also some uh, easy to handle. For example, this UV visible spectroscopy that can be used to identify the graphene oxide in short time. So UV visible, as you can see from this figure here, it was taken from my previous supervisor when he synthesized simplified Hammers methods. As you can see that there is an appearance of a peak at 229 to 233. This is the region, the range of graphene oxide peak that appear for UV visible absorption peak spectroscopy. So it happens due to the transitions of pi to pi anti bond that can be identified, uh, the transitions of C double bond C bonding. And then the second characterization that can be used to identify graphene oxide is the X-ray diffraction, which is XRD, in short call it SRD. So as you can see here, the SRD shows a very distinct peak that appear at 10.24 degree for graphene oxide and 25.56 for graphite flake. So this also the interlayer spacing values of graphite here is 0. 0.34 nanometer, and for graphene oxide is 0.87. And as you can see, there is an increment in the value of interlayer spacing. This is due to the introduction of oxidation functional group when we are introducing graphite with the oxidation agent. So that's why the interlayer spacing value is increasing. All right, the third one will be the FESM, field emission transmissions electron spectroscopy, or in short FESM. So from this FESM, what we can observe is that we can find the average lateral dimensions of graphene oxide increase as the ratio of potassium permanganate increase, as shown in this figure D. And as you can see, D showing the unsonication graphene oxide. So that's why the lateral dimension is quite bigger, can go up to 120 micrometer with the area up to 8,000 micrometer square. And for the A, B, and C, A, B, and C is actually different potassium content, potassium permanganate content, and also undergo sonications. That's why it reduced the size of the graphene oxide sheet. And the third tools that can be used is the atomic force microscopy. So based on the AFM, or atomic force microscopy, high profile analysis, the thickness of this graphene oxide sample is around 1.2 nanometer, which is equivalent to the one size of atoms. And this result has been consistent with the thickness of characteristic single layer of graphene oxide that has been reported previously. Okay, now we are look at to the demonstration of graphene oxide that synthesized by simplified Hammers method. So I provide here is a visual demonstrations for this preparation of graphene oxide via simplified Hammers method. So let's see together. Okay. Okay, I would like to dedicate thank you, credited thank you to my final year project for these preparations of video, because Mr. Zul Aiman for this is a part of his final year project for the first semester. So next we go for the conclusion. So from this simplified Hammers method approach, it's basically is hassle free, and the experiment is relatively safe, and we also can reduce the risk of having a danger cost, like example for explosions, and the mixture and also washing step are very simple and more straightforward, and we also can have almost 100% conversion yield from a graphite into graphene oxide. And this, the most important thing, the development of oxidation and reduction process is able for us to separate individually carbon layer and then isolated them without modifications of their structures or their properties. And these chemical reductions of graphene oxide is currently seems the most suitable method in order for mass productions of graphene. So chemical oxidations and chemical reduction process is a kind of promising and suitable method that can be used in order to have mass productions of graphene yield. So the overall synthesis route can be modified in order to fit our applications in the future. So this is a little background of my current research and also my previous research, that I'm using a chemical synthesis to oxidize graphite flakes into graphene oxide, and later on reduce into reduced graphene oxide with the compositions of different type of nanomaterial. I'm using metal base, for example. In this figure, I'm using gold nanorod, and also metal oxide base, and that I'm using is copper oxide and also zinc oxide. Some of it will be polymer. For example, in this research is the naphions, and this composite, a graphene-based nanocomposite, has been used for application in electrochemical sensing, where we introduce or we detect the chemical analyte, for example, nitride oxide and also nitride ion. So I end my presentation today by quote for a graphene oxide, a modern material with unique physical and electrical properties that could reshape our future. So thank you very much for your attention, and I would very happy if I can receive collaborations or contact from audience who want to work together on this project or upcoming project. So besides that, I'm also very happy to answer the questions from the floor, if any. Thank you very much for me.
Okay, thank you to Dr. Malinda for your informative sharing. So I would like to open to the audience if there are any questions that you want to ask to the Dr. Malinda. Before I forgot, don't forget to scan the QR code in order to obtain the certificate of participation. And for the next session that will be held in the afternoon. The session is on industrial webinar, and the speaker is IR Dr. Muhammad Shiraz bin Arif from Samdabi. And the title of the webinar on the afternoon session is Samdabi Plantation, R&D, Current Challenge and Future Prospect. And it will be held on 2 p.m. And the chairperson is Dr. Yasmin Abdul Wahab. So is there any question from the audience? Okay, I received one question from Muhammad Fazli Hamid. So the question is it possible to use graphite pencil lead, which is we obtain from the mechanical pencil instead of your graphite wire? So we have several diameters of pencil lead, mechanical pencil lead, which is from 1, 0.5, 0.3 mm. So let's say if we use 0.3, then can we obtain the graphene oxide, which is the originally from graphite pencil? Okay, thank you. Dr.
Okay.
Malinda?
All right. So thank you very much to Muhammad Fazli for the questions. Yeah, it's actually this is when you are talk about mechanical. This method we call it mechanical cleavage, where at the first beginning, the discovery of the graphene actually when these two Germany physicists, when he start to using Scotch tape to exfoliate graphite, which is graphite lead for pencils, and then to produce graphene. So yes, it is possible to use graphite pencil lead to uh, to form a graphene oxide, but it's up to you what type of technique that you want to use. Is either mechanical cleavage, or in my methods that I introduce here is more on the chemical oxidation method. And
Okay.
I think maybe I can add more. Uh, we also there is a this is like during our school, okay, secondary not secondary school, preliminary school, we have done some experiments of using uh, pencil lead in order to connect to electrode when you are connected to battery to light up the bulb, right? As you can see, when you use a very thick pencil lead to scratch on the electrode in order to connect it, you cannot connect the electric cannot flow. But when you exfoliate it by using Scotch tape, time by time you can see that the light start to light up. It's the same mechanical methods that we use to exfoliate graphite into graphene.
Okay, second question, Dr. Malinda, from Shazwani Amirah Saleh. So the first question is, if you want to use graphene from the waste material, just like recycling, can we use the same method from the Hamus method?
Waste material. Uh, yeah, this one you need to, first of all, you need to purify the waste material in order for you to remove uh, maybe apa non-carbon material. So you can do it, but you need to purify it first in order to have only carbon substitute. And then later on, you can use it chemical oxidation methods to oxidize your waste into a graphene or into reduced graphene oxide.
Okay, the second question from Shazwani, can we use the same method, which is Hammer method, if you want to synthesize graphene oxide from graphene instead of graphite? So the original source is graphene itself.
Okay, you want to produce again
Graphene oxide from graphene instead
graphene
of
oxide.
graphite.
Okay, all right. So meaning that you have your end product is graphene, but you want to produce graphene oxide, right?
Yeah.
Yeah, you we call it yeah, same oxidation. You just introduce as I mentioned earlier in the first beginning of the slide, we can introduce to the functionals group, for example, oxygen functionals group like amine group. You can introduce to your graphenes due through chemical chemical processes, and then it can produce a graphene oxide. So you can identify this uh, sample by using UVVs. Is very visible, very easy, and very you can obtain the result very shortly. For example, if you from graphene, you can see that the absorption peak is around 260 something nanometer, and when it's already been functionalized with the oxygen functionality group, you can see that the shift in it's already shifted into blue shift around 290 or 230. So the shifting can be determined in short time using UV visible.
Okay, next question from Said Hafiz. Dr. Malinda, is we change the different brand of graphite powder, then can we determine the, the quality of the graphene oxide output? So different source, different
Yes,
brands, then
correct.
can we get the similar quality?
Mm. Okay, this is yeah, we also were having apa tu thought this issue. Yeah, we if we are using different graphite powder, it also can affect the quality. For example, in terms of the size and also in terms of the shape. So like previously we are using a different brand, and we can see that the larger graphene oxide sheets that can be produced from the graphite source. But later on, when we are using a graphite powder with the fine structure, and the graphene oxide that obtains also having a very low or very small uh, surface area. So I'm suggesting, based on my previous research, I'm suggesting to use a graphite flake. There is a code there that we are referring to. Maybe you can search on the code. This one is 3061, graphite flakes, code number of 3061 that we last time purchased from a graphite mills company. Mm-hmm.
So the brand is from Graphite Mill.
Mm-hmm.
Okay. So is there any question to be asked to Dr. Malinda before we end the session? So if there is no question, so I would like to remind to all the participants to scan the QR code at the end of this session to obtain the certificate of participation. And don't forget at 2 p.m. we're going to have our next webinar. It will be the last session, which is on Samdabi Plantation R&D by IR Dr. Muhammad Shiraz Aris from Samdabi. So thank you.